So now we come to the magnetism section of the course. I expect you guys are pretty familiar with this, but if you want to brush up a bit, I'm going to go over a little tiny bit of the background stuff. If you'd like to review a bit more, you can check out the beginning of chapter 29 in night. The Wikipedia article about magnetism history is pretty good. It details about how magnetism has been observed by all cultures over all times, even though we talk about a lot of the contributions from European scientists from a couple hundred years ago, it has been observed kind of forever. There's a couple of neat things, but not really required. The bottom thing, the Nature of Things documentary, that's about the flipping of the Earth's magnetic poles. That's pretty interesting. It is kind of a long show, but if you have time to check it out, you might like it. So, why do we study magnetism? I guess I would say it's because magnetism is everywhere, it's all around us, and it's very relevant to our everyday life. So, magnetism is important in geology, it helps us study the nature of the Earth. We learn about astronomy through the magnetic fields of stars. We have magnetic fields all throughout our body, and for example, MRIs is all based on magnetic technology. Energy generation wouldn't really happen without magnetism. We use it in transport, in technology. So magnetism is everywhere, just like electricity is everywhere. So it's pretty important to study and understand magnetism. So just like charges have electric fields around them, and we represent those fields with electric field lines, magnets have magnetic fields around them, and we represent those fields with magnetic field lines. So here, if you look, you see I've got a little plastic jobby full of little tiny compasses, essentially. I'm going to lay bar magnets on top of them, and let's see what the field lines look like. So I put on my bar magnet, red is north, blue is south. The magnetic field lines go out of the north and into the south. They circle around the bar magnet. If I turn it around, the magnetic field orientation flips. If I put a south down and another south next to it, those field lines never cross, they never meet up. And then two norths, same thing happens, they kind of repel away from each other. And then a north and a south, we see the lines go from the north into the south. So this is a quick picture of what the magnetic field lines look like. And this is just a summary where I've robbed some nicely drawn images from the textbook. We see that the magnetic field lines go out of a north into the south. Magnetic field lines never ever cross because a field can't have two directions at the same time. Magnetic fields are weak where the lines are far apart, and the magnetic field is strong where the lines are close together. So just like there's an electric force between any two or more charges, there are also magnetic forces between any two or more magnetic items. I'll put a couple of bar magnets close to each other and we can see what happens with the forces. So when I put north next to south, they click together, so that was an attractive force. Let's just look at that one again. So they get pulled together, so opposite poles attract. If I try and put two souths together, they push away from each other. So like poles repel. That's kind of like what happens with the charges, where like charges attract and opposite charges repel. We see that magnetic force is action at a distance, and that's what we see whenever we have forces that are exerted by means of a field. And this force is, of course, measurable, and the force depends on the strength of the field and the separation of the two magnetic items. It turns out that our planet is actually like a giant bar magnet, where the geographic North Pole is close to the magnetic South Pole, and the magnetic North Pole is close to the geographic South Pole. So magnetic South and geographic North go together. Magnetic north and geographic south go together. Something that's kind of neat, and by all means try this at home, you can make yourself a compass just like some ancient civilizations did. If you can grab yourself a bar magnet and you can attach it to something that'll make it float. I used a couple of corks and some rubber bands. You pop it in a dish of water, you see that it turns around? It will line up with the magnetic field of the Earth and it will show you which way north is. So by all means, you can make your own compass at home. The thing I find really interesting is that a lot of animals use magnetic navigation. It's called magnetoreception, and what that means is that animals or organisms feel a magnetic field. So they just the way you can feel temperature or wind, some animals feel magnetic field. It's a weird idea, but there it is. It's still true. And then many organisms will either orient themselves to that field or use it for navigation. So I've got some different creatures here. The first is a homing pigeon. The homing pigeon uses magnetic fields to line up and know where home is, so it can follow the magnetic field lines. And then the little guy who kind of looks like a worm, that is a magnetotic bacteria. So those are little bacteria, they're really tiny, of course, and they live in the ocean, and they have magnetized bits of iron in their bodies. What happens to them is their bodies line up parallel to the Earth's magnetic field. These bacteria, they live in the ocean, and they tend to live near the bottom of the ocean where there's low oxygen. So if the water is disturbed, if there's some sort of disruption, a big fish swims by and they get forced upwards, they need to get back down to the bottom in the zone that they like. What they do is they follow the magnetic field lines to know where the bottom is, because they can't see, they can't tell, but they can feel that magnetic field line, and they know to follow that to get back down to the right spot. What else do we have? Salmon use magnetic fields to know how to get upriver to get home to spawn. Turtles, they follow magnetic field lines to get down to the beaches, okay, to get down to the water on beaches. Bats follow it when they're navigating. Field mice. Foxes, when they jump after prey, tend to jump in a northeast orientation, so that's kind of cool. Apparently, and I have not seen enough of this to know verify it for myself, but apparently fields full of cows will line up kind of north-south when they graze. And one last thing, dogs, I only have one dog, so not possible to do a real scientific study here. But apparently dogs, if they're off leash, they will line up north to south when they kind of do their business outside. So anyway, that's kind of a neat idea too. If enough of you guys wanted to get together and test it with your own dogs, that might actually be enough to get a study published. So there's a qualitative overview of a lot of what we're going to do with magnetic fields. The next bit we'll get into will be using some equations and talking about force and field and things like that. So here's one last summary slide. We've talked about most of this stuff, a couple of last points to mention. So magnetic fields have a symbol of B, and they have units of Tesla after Nikola Tesla, which usually we represent with a capital T. Something different between magnetic fields and electric fields is that while you can have a charge by itself, a single positive like a proton or a single electron, except for a negative, you can never ever have a magnetic pole by itself. So there are no monopoles. I'll add a but to that. Theory does suggest that monopoles exist, but we've never ever observed them experimentally. So I guess there's a Nobel Prize project for you. If you can find a magnetic monopole, I guarantee you will win the prize of that year. And last, our permanent magnets are actually magnetic because the electrons inside them, the electrons spinning, actually create a magnetic field. We're not going to cover that just yet, but we are going to come to that. So that's where permanent magnets come from. It's the nature of the atoms and the charges within the atoms. Let's begin looking at the magnetic fields around a current carrying wire, and let's begin with a story of how that was observed by a person.
So here's a replication of an experiment that happened by complete serendipity hundreds of years ago. Orsted was a lecturer, not that different from me, and he was doing a classroom demonstration, also not that different from me, where he had hooked up a circuit in a classroom. You know, something like this. He just had a couple of wires, it was hooked up to something. But in Orsted's experiment, what he was doing in class, he also happened to have a compass close by. And what he found when he turned up the current, that's what I'm doing now. See what happened on that compass? I'll turn it down. I'll turn the current back up. Oersted noticed that when he put the current through the circuit, the compass deflected. The compass was sitting next to the wire, and the compass moved when the current got turned on. So Oersted made the discovery in the middle of a lecture that a current carrying wire actually makes a magnetic field. That was pretty big news.
Oersted, of course, experimented with that until he figured some stuff out. So, one thing he discovered is that the magnetic field around a current carrying wire made big circles around the wire. What I've got here on the left is a 3D image. So, we have a wire that's supposed to be going straight up, and it's stuck essentially through a piece of cardboard that has iron filings on it. The iron filings are sensitive to magnetic fields, and you see they line up in circles around the wire. So Oersted figured out that the magnetic field around a current carrying wire makes big circles. And that's the picture on the left too. That's just a drawing that shows that the compass needles line up to show that the field is a circle around the wire. As we go through, we're going to try and continuously build the idea that electric fields and magnetic fields are interrelated, they're connected. So let's just have a very quick refresher about electric fields. We know that charges will feel an electric force when they're in an electric field. That means that a charge in an electric field will move, which means there's a current created. Okay, now we'll throw in on top of that that magnetic fields exist around current carrying wires. Oersted's experiment told us that the magnetic field around a current carrying wire made circles around the wire, and we drew that on the previous slide. Now, magnetic fields, of course, are a vector, so they have a direction. If we look at our circles, we'll notice that there could be two directions. Whoops, that was a very bad line for that last one. Try again. There's two possible directions. The circles could go around in a clockwise sense, or they could go around in a counterclockwise sense. Oersted found the directions using a compass. We can also find the direction using a right-hand rule. I copied a simulation from the St. Mary's University site. They have so many good things there, and it shows how to use a right-hand rule. So what you do is you take your thumb and you stick it in the direction of the current flowing in your wire, and then you just curl your fingers into a circle. That shows the orientation of our circle. That shows the orientation of our magnetic field. So let's assume that the current in our wire points straight up, just like it does in our simulation there. Then if we if we point our thumb in that direction, the magnetic field will come around in a clockwise direction. So it matches what we have in that simulation there. If the current pointed down instead, the direction would be in the opposite direction and it would go counterclockwise. So the picture we just looked at, that was a 3D picture, or a, sort of a side view of a 3D picture. So you've got an X, Y, Z coordinate system. We don't always want to go around drawing 3D pictures when we have magnetic fields. It's often pretty useful to do a two-dimensional adaptation, so to do a top view. So let's imagine we're standing above this wire and we're looking down at it. Well, then what it would look like is that the current would be coming straight towards us, and that's what I've got pictured here on the right-hand side. So the little yellow circle is us looking down at the top of the wire. So now this brings us into some 3D notation. If a vector, and current is a vector, if a vector is coming towards us, it's coming out of the page. We represent that as a dot inside of a little circle. That means out of the page or towards us. If a vector is going away from us, we represent that by a cross inside of a circle, and we say that that's into the page, and that means going away from Yes. This notation, historical reasons, it's like you're looking at an arrow or a dart. So an arrow has a pointy end. If the pointing end is coming at you, you're looking at the tip of the arrow or the dot. The end of an arrow has got flights on it. So if the arrow is going away from you, you're looking at the flights of the arrow and it looks like a cross. Okay, in our 2D adaptation, we're looking down at the wire, so the current is coming towards us. So that would have a dot inside of our circle, showing that the current is coming out of the page towards us. We do our right-hand rule, which means we take our thumb and we stick it out of the page towards ourselves. We look at what circle our fingers are making, and we see that it's going around in clockwise circles. So the magnetic field is represented by our blue circles, and the magnetic field at any single point would be a tangent to the circle. So for example, over here on the left, where the arrow points straight down, the magnetic field at that point is straight down. At the bottom of the circle, our arrow comes around to the right, so the magnetic field would point to the right. On the right-hand side, the little arrow points up, so our magnetic field points straight up. At the top, our arrows are coming around to the left, so the magnetic field is to the left. And it can also be at an angle too, of course. So here it's going left and down. So your magnetic field at any point is tangent to the circle. With the orientation given by the right-hand rule. Here's a summary of everything we discussed in the last few slides about finding the magnetic field using the right-hand rule and what the field looks like. One question I'd like to address that students often ask is about the left-hand rule. Some students do ask if they can use the left-hand rule instead of the right-hand rule. My first answer to that question is you're all grown-ups and I can't make you do anything. So if you use a left-hand rule, I can't make you change and I wouldn't even know anyway. However, our textbook and sort of all future textbooks and interactions you have will probably refer to a right-hand rule. A left-hand rule is an artifact of talking about current as electron motion. The convention is that we talk about current as a motion of positive charge, and that's where a right-hand rule comes in. If you go to electron motion as current, then that's where a left-hand rule comes in.